Hey everyone, let's continue learning about our transformation matrices. And now I'm going to talk a little bit more about the, let's probably zoom that in, about the projection matrix. This is a very important matrix because it's what converts from your camera space to to your screen space, which of course is my normalized device coordinates. Now what's really interesting to think about is up until here, we haven't really paid attention much to our units. So in the object space, we can determine whether plus or minus 1 or plus or minus 100 is the bounds of our object. That's fine. And then in the world, well, how much do you scale it up or down? With your camera, also, you can point it and you can look at somewhere, but how many pixels wide is it? That's not really defined. So the projection matrix is really important because it's the first time where we start to really specify the units in relation to our screen, okay? Now there are many ways to get into projection, and I'm going to actually come back to them a little later in the course. Many ways to do this. And the two most popular ones are orthographic, which I'll cover right now, and perspective, which is the most common one for 3D work. And I'll come back to that, and also projection more generally a little later. Now, as I just said, but I want to write this in my notes, since we convert from the world coordinates to camera, then to NDC here, your projection matrix effectively defines your coordinate system. This is where we do it. The coordinate system for the screen. Okay. For example, where is the center? Is center 0, 0, or is 0, 0 off to the side? What coordinate is the center, I should say? What are the bounds? You know, we've seen examples where I draw from minus 1 to plus 1. We've seen examples where I draw from minus 300 to plus 300. That's defined by your projection. So for example, in processing, you know, you can choose, actually, you can set it up of whether you draw from 0, 0 here to width, comma, height. That's a standard processing model you would have learned in a previous course. We can also do it this way, where you can see 0, 0 is at the center, right? And then 1, 1's up there, negative 1, negative 1. Notice that the y direction goes up this way, the y direction goes down. Or you could imagine 0, 0 at the center with 320 by up here, and then minus 320 down here. So you can imagine all kinds of coordinate systems that we've already seen in this course. Okay, and these are set up in the projection matrix. So let me first explain one projection to you. This is called the orthographic. Now, if you look up this online, I find that the orthographic projection, the only prescription is more what? The orthographic projection is defined in a really strange way, but I think it's actually not a hard concept to get your head around. So it has a few properties which help explain what happens. That, first of all, parallel lines, they stay parallel. This isn't true in 3D, right? Right? If I have train tracks, they don't go off into the distance like this. They converge. These are my train tracks. So these lines don't stay parallel once they're projected into the real world. Yeah, with orthographic, they do stay parallel. Things further away, stay the same size. They stay the same size as close-up ones. Okay, now this is getting strange. I'm gonna reorganize this. Just put that down there. There we go. Good. So things further away stay the same size as close-up ones. So what happens here with orthographic is instead of doing something clever, like with perspective, we just collapse the depth onto the camera. Right, so if I have, I'm going to draw a little scene here for you. Here's my screen coordinates with some camera off here looking, right? This is my camera. And then this is a screen, but in the world we have this triangle, and then really far away we have this circle. If it's looking straight at them, the triangle is going to appear here, the circle up here, and the far away circle down here. The close circle and the far away circle are the same size. You just take the depth and go squish it onto the screen. You just remove that depth component. Now I'm going to make a small note. I was just thinking in the back of my head, these parallel lines staying parallel, they do not, if you're into art, approach a vanishing point. Okay. So we just collapse this depth onto the camera. Okay. Now, come on. There we go. So let's look at what the orthographic projection might look like. I'm going to draw my screen coordinates here. Okay. Or I should say camera coordinates. So the way that we kind of work with the orthographic projection is we kind of work backwards. We imagine the projection we want, or the coordinate system we want. We imagine what coordinate system we want, and then we set up the projection to match that, and then we work backwards. Okay, I'm going to turn that off. So you can choose now. Where do I want my center to be? Do I want my center at the middle of the screen? Cool, right? I can choose that. What do I want my left comma bottom coordinate to be? Right there. What coordinate do I want that? -1, 1, +1, 1, -100, +200. And I think, what do I want my right and my top coordinate to be? This is, of course, x comma y, right? This is x comma y. So I choose these things up. I make these things up, or I choose them. And then there are three things we need to do to set up that projection. One is we move to the center. Right? We basically need to define where the 0, 0 is. Okay. Now remember, we're moving into NDC coordinates where 0, 0 is in the middle. So as you'll see, is if we choose the center to still be in the middle of the two sides, nothing changes. We keep the center in the middle. But in other projections, like up here, where 0, 0 is in the top left corner, then you need to set up that projection to define that. So we move to the center of where we want it to be. 2, we scale to the size of 2, 2, 2 by 2. Right? So the current scale is from left to right, right minus left. That's my scale. But I need to go to normalized device coordinates, which goes from -1 to 1. That's a range of 2. So -1, 1. That's my new scale. So I need to scale whatever I have, scale it down so that it fits in that space. And then 3, we actually, this is coming out of nowhere for you, we actually want to flip to a left-handed system. So remember, we have, if I'm in a right-handed system, right, X, Y, Z hits U. Z comes out of the screen. So if you look into the screen, the Z is negative. That's not what we want. In normalized device coordinates, let's avoid those. Normalized device coordinates are actually left-handed, so that Z goes right into the screen, okay? And that helps with a lot of the processing later, and we'll learn a little bit about that. But if we are moving to normalized coordinates, let's follow the norm. We need to flip to a left-handed system. Luckily, to go from the right-handed system to the left-handed system, we just invert the Z, okay? That's all that we do. So Z times equals -1. It's really easy. So the normalized device coordinates are in the left-handed system, so we need to go there because we want the positive Z axis into the scene, not behind us, okay?